All right, so let's discuss the key points, the real takeaway points that it's really important that you understand and recognize about logistic equations. So the differential equation starts off looking like this, and the logistic equation takes the form of that. All right. Another way that you can write this logistic equation, the differential equation part of it, is this. Okay, it looks different, but let's think about how we can go from one to the other. Let's take this original differential equation. We have ky 1 minus y over L. Right now, I can take that entire expression and multiply it by L over L. I'm really just multiplying by a form of 1. Okay, so I'm going to take this denominator of L and bring it out here with the k. So I have k over L times y. Now I'm going to distribute this L here and here. So I get L minus y. Alright, so here I have my y times L minus y, and the original k is now divided by L. So this k and this k are not the same values, but they have the same form. So this divided by L is just soaked up by the coefficient here that we have here. Alright, so you need to be able to recognize that both of these are logistic equation differential equations, or differential equations that result in the logistic equation. Okay, so in either case, dy dt, the differential equation, is quadratic in y. So in either case, if I distribute this ky through here, I have kyl minus ky squared. That is dy dt. Right, and here I would have ky minus ky squared divided by L. Right. So the differential equation itself is quadratic in y, and that quadratic would open downward. Right, because we have a negative coefficient on the y squared term. In order to see this differential equation and recognize it as the logistic equation, we really need to get it in factored form in order to find what the L and what the K are. Right. So when we find L, that's our carrying capacity. That's the given environment's ability to carry a certain number of organisms in it. That L is the carrying capacity. So if we're given a differential equation, we don't need to derive the logistic equation as we did on the prior page. It's a long process. You don't have to take the time to do that. You have to have these forms recognize the differential equation, go straight from the differential equation to the appropriate logistic equation, and be able to make this the proper conclusions based on that. Okay, a few things that come up really frequently. The rate of change of the population, that's dy dt, is always the largest when the population is half the carrying capacity. It's always, the dy dt is always the largest when y is half of L. Right, and y, the population, is going to have a point of inflection there as well. All right, that's important to remember. And just to kind of show you visually, if you take a look back at the first page of our logistic equation, you can see that the differential equation takes this form, and you can see that we have a point of inflection somewhere right in there, right, when our population is equal to half the carrying capacity. And we have a point of inflection here, and that's also the place where the slope is the steepest. The slope of the population is the steepest relative to time. So this is dy dt at its maximum right here at y equals L over 2. All right, so those are some of the really important things that you need to remember about the logistic equation.